Today we are going to see about overview of non-thermal processing technologies. The outline goes like this: the high hydrostatic pressure technology, pulsed UV light technology, pulsed electric field technology, and high voltage or discharge technology, cold plasma and ultrasound. The introduction about non-thermal processing technologies. So, they are mainly employed to ensure the sensory quality and nutrient values of food by employing short processing times and low temperature conditions. Okay. So, the moment I say what we have discussed in thermal technologies is the time temperature combination would be very much important. Time and temperature combination. So, this time temperature combination is very much important to maintain the lethality or to deactivate enzymes which spoils the food and also the killing of pathogenic and spoilage microorganisms. Alright. So, most of the thermal technologies, so we apply this time temperature combination for this purpose. So, what happens is, because we are always concerned about the killing of microorganisms, sometimes my food may get overcooked, right. So, when in the process establishment we have also seen, so I supposed to find the equivalent F value. So, that means even if the 12D process is enough to ensure the safety, so for all safety purposes I would go for extra 3 or 2D more. So, that means though it is said that 12D process is safe, so normally industries would apply more than that, maybe 16D process. So, the disadvantage of that is, what happens is, when you go for such a safer value, sometimes your food gets overcooked and your nutrient values will go from the food, right. So, to ensure this sensory quality and nutrient values, we thought about that how to do it with the lower temperature conditions in shorter processing time, so that my food will get a fresh look, right. So, it should not be cooked or overcooked. So, that is the way these non-thermal technologies are emerged with that motivation and still be used to enhance the food safety. So, that they are talking about, even though I am employing lower temperature and shorter processing time, I will ensure the required log reduction in terms of microorganisms. Right, and that way I will extend the shelf life of the food. And also the non-thermal technologies could inhibit the activity of enzymes in the food, such as lipooxygenase and polyphenoloxidase and peroxide and pectin extase. So, these are all the enzymes which indirectly or directly favors the oxidation reaction. For example, if you see here, so it catalyzes the oxidation of polyunsaturated fatty acids and lipids. So, these technologies will inhibit these kind of activities of the enzymes as well. So, this is also a oxidase, this is polyphenol oxidase, this peroxide. So, this non-thermal technologies here inhibit the oxidation of hydrogen peroxide, right, and this is pectin estrase. So, all these enzyme activity also get inhibited when we use non-thermal technologies. So, we have understood the mechanism how it happens during thermal technologies, right. We told that most of the nutrient reduction or the log reduction of microorganisms follow the first order kinetics, right. So, the kinetics involves temperature and time combination, but here I am not using the higher temperature. So, that means if it is not a function of temperature, then by which mechanism my log reduction of organisms happens, right. So, that is by changing the cell membrane structure to remove the regulatory function of the microorganism. So, for the regulatory function of the microorganisms, the essential thing is the membrane structure. So, I will alter the membrane structure so that some of the regulatory function in the microorganisms get changed. So, that way microorganisms get killed. And another one is destroying the genetic materials. So, genetic material here is DNA and RNA, right, to cause metabolic disorders in the microorganism. These two are the principles behind the killing of microorganisms in non-thermal technologies. We have just seen the thermal technologies, the disadvantages, undesirable changes both in the nutritional and in the sensorial properties of the food. Sometimes if it gets overcooked, I do not feel the taste as well, right, and it is sometimes the texture is not pleasing to have that food, right. So, these two are main disadvantages when using the thermal technologies. The increased consumer interest in high quality food with higher nutrient and fresh like sensory attributes. You will get this in thermal technologies as well, but mainly it is done for high nutritive value and fresh like sensory attributes, which led to the development of number of non-thermal processing technologies alternative to conventional heat treatments. So, the first one we have already seen in outline, which is nothing but a high hydrostatic pressure, which has the potential to improve the energy efficiency and sustainability of the food production, and pulsed electric field technology, which is also a non-thermal technology, which provides minimally processed, safe, nutritious and fresh like foods. And commercially applied for preservation of liquid foods, this PEF mainly applied for liquid foods or as a pre-step for solid food processes such as drying or extraction. So, before going for these solid food processing technologies, PEF is applied. And other one what we have seen in the outline is high voltage or discharge and cold plasma. So, these are also proposed as an alternative to conventional thermal processing treatments, and HVAD consists in application of electricity to pasteurize the fluids by rapidly discharging electricity through a electrode gap. So, you have two electrodes in between your fluid is flowing. So, you apply the electricity, so by which the electrical charge is conducted to the fluid. So, in that way it kills the microorganisms, generating intense waves and electrolysis. Electrolysis means the lytic of the components. So, that means you are breaking down the components, thereby inactivating the microorganisms. Unsuitable largely because electrolysis and the formation of highly reactive chemicals occurs during the discharge. So, mainly the electrolysis happens in the microorganism and they get killed. The same is applicable for food as well. For example, how we compared in the thermal technologies, though I am applying a high temperature, microorganisms gets killed, at the same time my nutrient quality also get affected. The same way, if you are using HVAD, that is nothing but a arc discharge, it is not only killing the microorganism, it also promotes the electrolysis in the food products, right. So, that is nothing but a liquid food products when I am pasteurizing. So, what happens when electrolysis happens in the food, there may be a highly reactive chemical formation, or sometimes the nutrients also form free radicals. So, that is unwanted thing in the HVAD process. Effectiveness of plasmas for killing microorganisms is well established. However, nutritional and chemical changes in plasma treated food are required to accurately assess the effect of plasma treatment on product quality. Actually, in all 5 whatever we are going to discuss today in the class will have this disadvantage, because the mechanism of microorganism get killed is not clear cut, right. So, no one told okay, so this is what happened in that. There may be a theories, different theories. So, it is proposed, but there is no confirmation, okay, so this is the correct mechanism which is happening in that particular non-thermal technologies. For that the literatures were very limited, okay. So, it is not well established, that is what it is said. It is not that it is established, it is not well established. And also when such kind of the free radical formation, we need to be extra careful because the food is to be consumed. So, we do not want any extra byproduct formation or any electrolysis happens during the food processing. And shelf life, and to confirm that no harmful byproducts are generated. This is what I told. So, we need to ensure when we apply non-thermal processing technologies. So, this is the main disadvantages, often technically difficult to apply into the production practice because very few studies are there confirming their food safety, and they are expensive because the electric discharge or cold plasma, or if you see the high hydrostatic pressure, everything is high pressure. To maintain high pressure, high temperature equipment and training the personnel, it is very much difficult. And consumer acceptance and safety issues, right. The moment you say I am using the electricity for processing, then we are also skeptic about whether any byproducts produced during the non-thermal processing or not. So, the consumer acceptance also one of the main criteria, and few resources and limited expertise to develop and implement novel emerging technologies. This also stops the non-thermal technologies widely applied in the industry. The first technique is high hydrostatic pressure technique. So, this is applied for preservation of wide range of foods, meat, fish, seafood, dairy and vegetable products, ready to eat meals, but also for some fermented products such as beer and wine. So, all this technology is among non-thermal technologies. This technology is well established and some of the industry also adopted it. And the pressure acts mostly instantaneously and uniformly in all points of the food, which mean that no matter the food shape or size affect the pressure, and the pressure is evenly distributed according to Pascal law. So, what it means is, so if you see the pressure concept, so the pressure increases with respect to depth, right, and if you see at particular height, the pressure is evenly distributed. So, that we call it as a hydrostatic equilibrium. Hydrostatic equilibrium. Right. So, at certain height the pressure is equally distributed, it does not matter which size, which shape of the food is there. So, right. So, that is nothing but a Pascal law. So, with this principle only high hydrostatic pressure technology works. So, the pressure range we apply here in the HHP is 300 to 800 megapascal. The mild temperature range is 5 to 35. Remember, this is when we apply initially, right. So, due to adiabatic heating, because the chamber is closed chamber, during processing it may rise up to 55 degrees centigrade due to adiabatic heating. Adiabatic heating is without heat transfer to the environment, the heat is builded up within the chamber. So, that is nothing but adiabatic heating, right. So, due to which the temperature may increase up to 50 degree. Combined with different time periods, in general minutes, that should result in an inactivation of microorganism. So, that this pressure and temperature combination with a certain period will take care of the inactivation of microorganisms. The microorganisms inactivation mechanism with HHP takes place at low energy and does not promote the formation of unwanted chemical components or free radicals that can result when food is irradiated. If you see pulsed UV light or pulsed electric field, so there is a irradiation of energy is involved, but that is not here in the HHP process. So, that means there is no formation of unwanted chemical components is there compared to other irradiation technologies. So, this is the basic diagram. So, what happens is, this is your closed pressure chamber, right. So, here your food material is there. So, this is a sample support. So, using the pressure pump, the water is pressurized inside the chamber. So, once the required level of pressure, for example, so if you are doing it with some 700 MPa, right. So, once the 700 MPa pressure is reached, so this is the pump is stopped, right. So, then we already told, right, it is a certain time period, right, it is kept. So, that means the 700 pressure is applied equally on the food material. So, that is nothing but due to Pascal law, which is nothing but a hydrostatic equilibrium. Then once the this time period, after keeping it in this particular time period, so using the water release valve, this is decompressed in the sense depressurized, the chamber is depressurized, and this is a heating and cooling medium, this is a jacket around the chamber. So, that is the way this high hydrostatic pressure works. So, many processes happening simultaneously, but are not completely known. What is this process? This process they tell in terms of killing of microorganisms. Killing of microorganisms. So, as I told, there is no clear cut definition, okay, by which this mechanism only my killing of microorganism happens. There is no well established theory for that. So, it happens due to alteration of cell membrane, denaturation of proteins, which includes enzymes as well, and the changes of cell morphology, which are thought to be a primary reasons for microorganisms damage, and it is not like one particular principle. High pressure alters the membrane permeability and causes the leakage via internal and external membranes, which has been proved by increased sensitivity of the cells to sodium chloride and bile salt and leakage of ATP after HHP treatment. So, after the HHP treatment, the products were analyzed, and it was well understood that the components which has to be inside the cell membrane were out of the cell membrane, and the products whatever there in the outside of the cell membrane were also went inside. So, that means the membrane permeability got changed, right. So, the membrane permeability normally what happens, it permeates certain component, not permeates certain components. So, when this got changed, we do not know, we are not sure what are all the inside components came out of the membrane and what are all the outside components went into the membranes, and also it was proved that the cells are sensitive to NaCl salt. So, that means, so there may be some compositional changes, and also the ATP, adenosine triphosphate, so that was found in the sample after HHP treatment. So, that means the leakage happened through the cell membrane. HHP can denature protein structure and corresponding enzyme activity. So, these were the theories proposed after HHP treatment by which the microorganisms get damaged. In addition, HHP causes changes of morphology and inner organization in cells that we have seen, and altered the distribution and degradation of DNA and the destruction of ribosome have been found after the HHP treatment. And many vegetative bacteria including spoilage and pathogenic microorganisms, yeast, molds and viruses are sensitive to HHP, and however, it should be noticed that the spores are very resistive to HHP, right. Even in the thermal technology we have seen, right. So, most of the thermal technologies were able to handle the vegetative forms of the spoilage as well as pathogenic organisms, but very few thermal technologies only able to kill the spores form of the microorganism. The same thing is applied for HHP as well. So, it is told that, so many vegetative bacteria which includes spoilage as well as pathogenic and yeast, molds, viruses get killed, but it is noted that the spores of Clostridium botulinum can still survive. This is we discussed in many classes under extreme conditions of 827 megapascal for about 30 minutes at 75 degree. Even applying this high pressure and high temperature for about 30 minutes, which is also nothing but a high time, the spores of Clostridium botulinum did not get killed. It has been demonstrated that the gram-positive bacteria or cells in stationary growth phase tend to be more resistant to high pressure. So, this is gram-positive bacteria. If your food is prone to gram-positive bacteria or cells, then this technology may not work better. 600 megapascal pressure is a threshold value and is also considered to be economical and microbiologically safe for achieving pasteurization level if it is combined with the temperatures in the range of 35 to 55 degree. So, 35 to 55 degree and 600 megapascal pressure is enough to pasteurize the food which are microbiologically safe. The critical factors are pressure level, time at pressure, time to achieve treatment pressure, adiabatic heating, this I have told, and decompression time. So, after the process is finished, how much time I am taking for decompression, and treatment temperature, product's initial temperature, pH, water activity, composition of the product, packaging material. This is very much important criteria, because when you are applying the high pressure, then you need to take the pouch materials or pouch packed materials, and it should withstand that high pressure. The packaging material should withstand the high pressure processing, and extrinsic factors prior to processing and during storage and distribution. HHP has the potential to produce high quality food and display characteristics of fresh products and are microbiologically safe. Important advantages, nothing but it is subjected to high pressure with or without packaging. So, both way we can use, but which in former case eliminates the possibility of post treatment contamination, right. So, whatever the thermal non-thermal technologies we say, we feel it, the thermal technologies were best in terms of microbial damage, because the mechanism is well understood. But here what they wanted to tell is, when you are subjecting a high pressure, it may be done with or without packaging, but if you do it with packaging, the post treatment contamination we can better avoid. And pressure treatment alone is often not sufficient for substantial reduction of viable spore counts, this we have seen. So, as some spores of some species seabird were found to survive up to 1200 megapascal at room temperature. So, in that case, some of the species spores can survive up to 1200 megapascal at room temperature. So, this only HHP may not be microbiologically safe. So, in that case we also combine temperature as well as the pressure process. So, combining pressure processing with other hurdles have been suggested. In that case, increase of temperature as well as pressure both, and increase in exposure time. But also we have seen in the previous slide, even if you apply 827 megapascal 30 minutes at 75, still spores of Clostridium botulinum survive, right. So, that is where it is told, either increase both pressure and temperature, or increase exposure time, or high pressure in low pH environments. So, this we have seen. So, low pH environments are microbiologically safe, combination with some antimicrobial agents. So, that also it may be tried along with high pressure processing. Along with high pressure processing, you increase temperature as well, or go for increment in exposure pressure, or lower the pH, or add some outside antimicrobial agents. The simultaneous application of high pressure and high temperature treatments can produce undesirable effects. So, we told the solution here, the increase of temperature and pressure, but what is the disadvantage? Again, loss of barrier to oxygen and delamination phenomena in the sense. So, you have a packaging material. So, when you apply high pressure and high temperature, there may be a forming layer. For example, if some crack will be there, so you will see different layers of that. So, that is nothing but a delamination, and unacceptable modifications in the integrity of packaging structure, that also happens. And selection and optimization of packaging structures for HHP processing are of extreme importance. I have just to mention that. In terms of correct processing, shelf life enhancement, economy, marketing, logistics and distribution. So, for this one thing I would like to take an example from that. There was some case study in some of the food industry, when they were storing it after the particular thermal processing, they found this contamination, right. So, in the contamination, they supposed to throw that particular batch, but still when they were inspecting what was the reason for contamination. So, they found that in the pouch, when they were sealing it, there is one particular hole due to the sealing machine rearrangement, right. So, for example, while sealing the packet, there were another extra line happened, due to which there is some damage happened during the sealing. So, through which the contamination happened. So, that is what here it is mentioned. So, it is the packaging structure is of very much essential when you apply HHP, because even in the sterilization we have told, right, that when you switch over from heating to cooling, if there are pouches, there will be a pressure imbalance inside the pouch material and outside the pouch material. So, to compensate that, we use compressed air over that to give the cushion effect. So, here also we are employing a high pressure. So, we need to be extra careful about the packing structure. And important drawback of the HHP at present time is the cost of this technology due to high pressure processing. We need to take care of all the control when we apply the high pressure. This process should not be confused with high hydrodynamic pressure process. So, this is another process. So, actually high hydrostatic refers to the liquids and pressure in a liquid or exerted by a liquid and immersed object. So, that means this HHP technology will be used for static mode in the sense, if you see, so you have a food particle here around which water is there at high pressure, or so this comes under the submerged objects under liquid, right. So, either it will be applied to pure liquid. If the food is liquid products, then the pressure is applied on the liquid, or if it is a solid product, so you are using the submerged object within the liquid. So, based on these two mechanism, HHP works, but hydrodynamics refers to the flow of fluid, right, and the force acting on the solid bodies immersed in these fluids. So, when the fluid in motion, it is called as high hydrodynamic pressure technology. HDP is novel technology used to extend the shelf life of meat products, in particular for tenderizing meat using shock waves from the underwater detonation of explosive material. So, this detonation of explosive material, when it is in underwater, it creates the shock waves. So, this pressure of shock waves is used to process the meat products in HDP technology. The effects of HDP treatment on further processed meat products are not fully understood. Additional studies on processed meat products of various textures are necessary to determine the effect of HDP. So, this mechanism is not well established. So, HDP treatment is at its nascent stage. The second one is pulsed UV light. So, here what we are going to use is in the white light of spectral band 200 to 280 nanometer. So, this range of spectral band from the white light we use as a UV light to inactivate the surface microorganisms using short pulses and often intense broad spectrum. So, short pulses in the sense, for example, so you have a wave, so this is time, right. So, how my pulses goes with respect to time. So, at particular time, how much intensity of pulses is being applied on the particular food product. So, that is what it is called pulsed, right, pulses with respect to time. Each pulse or flash of light lasts only for few hundred million or thousands of a second, but the intensity of each flashlight is 20,000 times that of the sunlight at sea level, which contains some ultraviolet light as well, right. So, it is applied on specific time, but the intensity of this UV light is 20,000 times what we see in sunlight at normal sea level. The deoxyribonucleic acid, which is nothing but a DNA in the cells, absorbs this UV light to form photoproducts in DNA, which interrupt the both DNA transcription and translation, and then leads to the cell death. This is not very common in the DNA transcription and translation in the normal microorganism regulatory function. But the moment the microorganism sees the UV light, it starts absorbing for its photoproduct synthesis. So, that way this transcription as well as translation of DNA gets changed. So, that is where the cell death happens. So, what are all needed? So, by name itself you might have understood, I need one pulse generator, treatment pulse generator, which is nothing but a timing control and trigger generator. Pulse generator you need. So, to power this unit you need a power unit to generate high pressure electrical pulses, and also treatment chamber to transform the light sources to high power light pulses. So, the treatment chamber as well as the pulse generator and the power unit to power all the units, and timing control and trigger generator. So, this is the basic diagram. So, here you have a power supply. So, it is given to energy capacitor unit. So, this is given to flash lamp, mostly xenon lamps. You have a reflector over here, it is a stainless steel most of the time. So, what its function is to trap the UV light inside the chamber, inside the treatment chamber. Here is your sample and this is the sample shelf. So, which has the vertical regulatory mechanism, so that this distance between the pulse created from the source and the food particle is very much important. So, this vertical regulatory mechanisms helps in that. For example, if I have to maintain 5 centimeter where the sample shelf should be, or if I have to maintain 2 centimeter where the size of the sample should be. So, by that we can also regulate the intensity of the pulse. And this is another way of treating the food using pulse UV light. So, this is a lamp. So, from which your UV light is coming up. So, this is the shelf, this is the target food product or food sample. So, you have a time indicator here, time setting button and power switch, power system. What happens is photochemical, photophysical, photothermal. Photothermal in the sense you normally know, right, when you have a lamp it is on for certain time. So, if you touch it, it will be hot, right. So, that is nothing but a photothermal effect. Due to this UV pulses, the food also gets heated to certain extent. And photochemical we just have discussed, right, the DNA absorbs the UV light and it synthesis the photo products. And photophysical is sometimes when the UV light is absorbed by the DNA, there may be a changes in the cell membrane activities, cell rupture also can occur. So, that is nothing but a photophysical mechanism. Pulsed UV light which has 200 to 600 nanometer treatment can effectively inhibit the Penicillium racqueforti and Listeria monocytogenes derived from the packaged and unpackaged cheeses. These are all examples. So, how this technology is being employed, and is also employed in vacuum packaged chicken breast, which the reduction of salmonella was 2.5 log CFU per centimeter square after the treatment of 60 seconds at 5 centimeter respectively, right. And while without changing the chemical quality and color of the sample using UV at 5 to 13 centimeter for about 5 to 60 seconds. These are all examples. So, what are all the microorganisms and what are all the food products are processed using pulsed UV light. So, these are all just example how much is the distance between 5 to 13 centimeter distance between the pulse and your food sample. So, this is the time limit. And cooked meat products, freshly cut mushrooms and surface of the knives which used for cutting the meat were also processed using pulsed UV light, and juices and milk also comes under that category. So, this light can affect the color and texture of the foodstuffs depending on the energy dosage and the distance between the lamp and the surface of the sample. So, if you increase the distance, there may be a good killing of microorganisms, but that also affects the surface texture of the food. Due to shadow effect caused by the rough and uneven surfaces, the crevices or pores of the foodstuffs, the effective radiation dosage for microbial inactivation can be reduced, resulting in unsuitable treatment for cereals, grains and species. So, what does it mean? So, if I have a food particle, so it has a pores kind of thing. So, inside the pores your UV light may not have got inside the pores, right. So, that the contamination what is there in the pores, it is lost long. So, it cannot be treated using pulsed UV light. So, when you have such a foodstuffs with the pores or crevices, it is better to avoid using this technology. Pulsed electric field, it is same as that of the UV light. So, there you used a lamp to create a pulsed UV light. Here you use the electricity to create a pulsed electric field, and which preserve the liquid and semi-liquid nature foods to increase their shelf life. And also the important thing is, so you can process liquid semi-liquid food, but it should not contain any air bubbles, because otherwise it will go for gas ionization process as well. It presents several advantages over conventional treatments. One is the better retention of flavor, color and nutritional value, improved protein functionality, increase the shelf life and reduce the pathogen level, which involves discharge of high voltage electric short pulses. There it is a UV light, here it is a high voltage electric short pulses, which causes the transitory or permanent permeabilization of the cell membrane. So, the mechanism here used to damage the microorganism is permanent permeabilization. So, short time electric pulses 1 to 100 microseconds in different ranges of electric field intensity. For example, 0.1 to 1 kV per centimeter, which is for reversible permeabilization in plant cells. 0.5 to 3 kilovolt per centimeter is used for irreversible permeabilization. 15 to 70 kilowatt per centimeter is used for irreversible permeabilization of microbial cells. The organisms treated here is Escherichia coli, Staphylococcus aureus and Bacillus subtilis. So, this is the basic diagram. So, here you have a treatment chamber. So, you have a PEF generation here. So, generated PEF goes to treatment chamber. You have untreated liquid food sample, so which is pumped through pumps, and here it is a flow meter which measures the flow rate, and it goes to temperature control which measures the temperature, and it is fed into the treatment chamber. This PEF generation is taken care by the control and monitoring system, and after that it is getting cooled, and after measuring the temperature it is collected in the treated sample tank. Accepted mechanism is breakdown of cell membrane. We have already told permeabilization. The pores on cell membrane are formed by high intensity electric field pulses. So, what happens in UV? The microorganisms absorbs the UV light, and by which the photo products were formed in the DNA molecules, but that is not a normal regulatory function of DNA. So, due to which translational transcription mechanisms of DNA gets changed for that particular microorganisms, that is the way it gets killed. But here what happens is, here the cell membrane absorbs this high intensity electric field. So, that way the pores are generated in the membrane, so which causes further the permeable nature of the outside components to inside the cell, and components inside the cells comes out of the cell membrane. With the increase in the number of pores, loss of cell content, intrusion of surrounding media occurs, which is also called as cell electroporation. So, pores, right, creation of pores using electric field, that is nothing but a cell electroporation, which depends upon electric field intensity, treatment time, temperature, pulse width, shape, electrical conductivity, pH and intrinsic factors of microorganisms such as type, size and microbial load and growth stage. Everything is a important factor when you apply PEF technology. And successful application of the PEF treatment depends upon biological factors, cells type, size, shape and cell density, arrangement and cells position, dielectric breakdown. Dielectric breakdown is nothing but how the components get broken when application of electric field is happening, and physical chemical property changes of the food, conductivity, pH and ionic strength. Advantages is PEF processing inactivate microorganisms with minimal or no effect on the quality attributes of the food. Retention of the fresh aroma and flavor of the food. Efficiency is better than traditional thermal methods that take long periods of time. It is the fact that spores of microorganisms are able to survive PEF food processing. Spores, till now we have discussed 3 technologies: pulsed UV, pulsed electric field and HHP. None of them could take care of the spores. It has not been optimized because adequate research has not been done to justify the use of these systems in the food processing industries. It is not that no industries is using, there are industries using this non-thermal technologies. Since the kinetic mechanism of the killing of microorganism is not well established for these non-thermal technologies, it will be very difficult to employ in the higher scaled up process in the industries. There is limited commercial availability of PEF processing systems because of the high initial cost. Cost is also another common disadvantage in all the non-thermal technologies. The next one is high volt arc discharge. So, this is used in many areas such as biochemistry, biology, medicine and microbial inactivation of food already, and it is also used in biocompounds extraction from different products. Main feature is that this generation of strong dynamic shock waves generated by the electric arc. It creates the electric arc which further creates the shock waves. Those shock waves act on the food particle and it kills the microorganisms. The arc discharge leads to multitude of physical and chemical effects. The high pressure shock waves can induce the bubbles cavitations which can create strong secondary shocks with very short duration. These shocks can interact with structures of the cell. So, what we told, electric arc which further creates the shock waves, high pressure shock waves. So, this high pressure shock waves leads to cavitation. Cavitation is the process when the local pressure is reduced, there may be a formation of bubbles. These bubbles collide with each other and forms the cavitation. Right. So, this cavitation further produce the secondary shock waves. So, this secondary shock waves are reason for the killing of the microorganisms. So, that is the main principle behind the HVAD process. The phenomenon results in mechanically rupture of the cell membranes that accelerate the extraction of intracellular components. So, intracellular components comes out of the cell membrane and the voltage arc discharge prompts the formation of highly reactive free radicals. So, this is important, right, from chemical species in the food such as oxygen, right. So, it forms the highly reactive free radicals. So, these free radicals are toxic components that serve to inactivate certain intracellular components required for cellular metabolisms. So, these free radicals are toxic components that serve to inactivate certain intracellular components. See, this is two way around, right. One is it forms reactive free radicals in the cell structure of the microorganisms. At the same time, it also create such free radicals, it may also create such free radicals in the food particles as well. So, in the microorganism side, it is the advantage for us because these free radicals changes the cell function and regulatory function. So, that way microorganisms gets killed, but in the food side it is unwanted one if it creates any reactive free radicals. The bacterial inactivation was not due to heating, but mainly due to irreversible loss of membrane function as a semi-permeable barrier between the bacterial cell and the environment. The formation of toxic components, which is nothing but oxygen radicals and other oxidizing components, was noticed. The major drawback is contamination of the treated foods by chemical products of electrolysis, this I told. So, if it is done on the microorganism side, it is advantageous for us because that is the way microorganisms gets killed, but it also does the same thing in the food particle side as well. The disintegration of food particles by shock waves is another disadvantage in HVAD process. The next one is cold plasma technique. The cold plasma, this you might be knowing how to change a solid to liquid, liquid to gas. So, the cold plasma comes here. So, what happens is when the gas is heated, it gets ionized. So, that is the way plasma is created. When it is deionized, it comes back to original gaseous form. So, this is the generation of cold plasma. Right. So, generation of cold plasma. So, there is a AC power unit through which the high voltage is given to the electrodes. So, between these electrodes your carrier gas is flowing. So, that is the way gas is getting ionized, right. The energy is given by the high voltage AC source to the electrodes. So, from there the gas ionization happens between the dielectric barriers. So, this is the way the creation of cold plasma, plasma generation happens. So, this setup is given to the treatment chamber. So, that probably here we are seeing. So, this is the gas system through which gas is coming here. So, this is the pressure system to maintain the pressure level. So, this is your high voltage AC current. So, these two are electrodes. So, this is dielectric barrier. So, through which when the gas is flowing in between, then it creates the ionization, which is nothing but a plasma. So, this is fed into the treatment chamber where your food samples are kept. The CP is a ionized gas, cold plasma, which comprises of large number of different species. There may be electrons, positive and negative ions, free radicals, electrons, gas atoms, photons, all are generated during the plasma generation, and it is suitable to be used for the processes for which high temperature is not recommended. CP could be employed in inactivation of microorganisms on the surface of fresh and processed food, and the accumulation of charged particles can rupture the cell membrane, and oxidation of the lipids, amino acids and nucleic acids with reactive oxygen species and nitrogen species cause changes that lead to microbial death or injury. The same way what we have seen in the HVAD. So, here also the oxidation of lipids, amino acids, nucleic acids happens. So, that way it alters the cell regulatory function, and that is the way microbial death happens. The contribution of mentioned mechanism depends upon the plasma characteristics and the type of the microorganisms used. So, we have seen one example, right, Clostridium botulinum, even if you apply 827 megapascal at 75 degree, the spores will not get killed, but the optimally microbial safe pressure for HHP is 600 megapascal itself. So, even if you apply high pressure, certain organisms will not get killed. The same is applicable for cold plasma as well. It depends upon the type of organism. The application is decontamination of raw agricultural product of apple, lettuce, almond, mangoes, melon, and egg surface and real food system, which is nothing but a cooked meat, cheese, etc. Key limitation: early state of technology and development, variety and complexity of the necessary equipment, and largely explored impacts of cold plasma treatment on the sensory nutritional qualities of treated food. It is unexplored, largely unexplored. The treatment must be proven not to have negative impact on the organoleptic and nutritional properties of the food. It should be proven, right. So, why it is, we have already told, since it creates all organoleptic changes in the cell functions, but also it is also responsible to create such a organoleptic changes in the food as well, but that is unwanted for us. Because we supposed to maintain the nutritional level of the food. So, that is the way this cold plasma is disadvantageous, and studies to specify the extent in which CP affect the chemical and nutritional properties of food and shelf life. So, that is very much needed, and safety and cost aspects to apply into practice the CP, and for scaling up this technology in food industry is not that well established, So, this we have seen already. Another is ultrasound. Ultrasound is nothing but whatever we could hear. So, beyond that level, that is nothing but a ultrasound technology. So, this happens due to cavitation phenomena. I have already explained you, shear disruption, localized heating and free radicals formation. So, this is the way the microorganisms gets killed. The propagation of ultrasound in the medium creates a series of compression, and through which, due to compression, the damage of microorganisms happens equivalent to HHP. When the energy reaches the certain point, the rarefaction will exceed the attractive forces among the molecules. Rarefaction is nothing but decompression. followed by the generation of cavitation bubbles. I have told when the pressure is reduced, locally reduced, the formation of bubble happens. So, that is the way then they get colloid and that is the way cavitation forms. Unstable bubbles collapse violently and produce outward propagating shock waves which can destroy the cell walls of the microorganisms or break polymer chains easily. The effects can also lead to the breakdown of water molecules causing highly reactive free radicals. It may be generated in the oxygen species as well and water molecules as well. So, which is nothing but H2O will become H and OH dot, there is a free electron. So, free radicals. These free radicals can modify or damage the intracellular components including DNA. So, remember this happens at the microorganism side as well and food side as well. So, this kind of free radicals may be happening at the food side as well, but that is unwanted. So, at that particular ultrasound level, at that particular time, it should only form a free radicals in the cell functions of the microorganisms, but not on the food. That is the optimization level, we need to be extra careful. It depends upon the ultrasonic intensity, frequency, temperature, processing time and which waveform we use, pulsed or continuous waveform. Pulsed I have explained you, this is the one of the example. Continuous means so kind of sine wave, right. And the microbial species and growing phase, this is also important. So, here are some application and treatment conditions and with which principal ultrasound works and what are all the advantages. For example, I will just take up 2-3. One is I will take up the sterilization. The frequency of ultrasound used is 20 kilohertz and the energy of ultrasound is greater than 1 watt per centimeter squared. So, the principle is thinning of cell membranes, localized heating and production of free radicals by which your microbial damage occurs, and advantage wise it improves the quality of foods at lower temperatures. And another example maybe we can take the cooking. The frequency is same frequency 20 kilohertz and energy is greater than 10 watt per centimeter squared. It improves the heat transfer in the cooking and reduce the cooking time and increase the quality of the food. For example, how we cook in the normal LPG stove and microwave, right. Here the ultrasound improves the heat transfer and reduce the cooking time and increase the quality of the food. So, other applications and treatment conditions, principal advantage, you may refer the references what I have given, from there only it is taken, this table is taken. And this table compares all the technologies whatever we have discussed. For example, if I take high pressure processing, which is nothing but HPP. So, typically the pressures between 200 and 400 and the temperature is less than 50 degree. So, this is the description of the process and it is independent of food geometry, we have already told. It is working under the principle of hydrostatic equilibrium. So, it does not matter which food geometry we are applying, and equipment size and operator parameters are important, and temperature and treatment time is also important when we apply HPP. So, the permeabilization of cell membrane is the mechanism by which the inactivation of microorganism occurs. Used for packaged foods or bulk foodstuffs, the HHP is used. And if you go for cold plasma, it is typically the barrier glow discharge between the two parallel electrodes, right. So, we have seen between the electrodes the carrier gas is flown. So, through which the plasma is generated. The treatment conditions depends upon gas pressure, type of flow and frequency and power of plasma excitation, everything are matters, and gas composition also critical factor, and destruction of lipid bilayer of the cell membrane happens in this CPL and used for surface of the raw products and packaging materials. So, you can see for other processes as well, though we have discussed in the class. So, this gives you the short and crisp description of the process and critical factors to be considered and mechanism of inactivation and their applications. So, this compares the strength and weakness of the each factor. For example, if you take HPP, it's high pressure processing. Somebody says the high pressure processing, there are two categories. One is high hydrostatic pressure and high hydrodynamic pressure technology. To please don't be confused with high pressure processing can be done in two ways. One is high hydrostatic pressure, that is mostly applied for static fluids, and high hydrodynamic pressure technology is applied on motion of the fluids, right. So, these both comes under the category of HPP. So, it does not matter whether it is a HPP or HHP or HDP. The principle behind is bit different, because HHP works on Pascal law, HDP you are doing it in the flow of liquids, right. So, do not be confused with these three terminologies. The strength is wide range of microorganism inactivation, including spoilage or pathogenic bacteria, molds, yeast, fungi and viruses, preservation of taste, nutrient and color, minor negative effect on sensory quality, shucking meat from shellfish and easy to commercialize and energy efficient, weakness wise limited on spores nothing can be done, and expensive equipment because of high pressure and batch process and limited packaging option. Okay. And if you see cold plasma, this we have already seen, right, wide variety of microorganisms, low temperature, rapid and effective. So, if you see weaknesses, low penetration depth, some alteration on sensory quality as well, possible residues on the food because we are using CP. So, this forms the free radicals. So, there may be a residues on the food as well. So, this is weakness. So, for all the technologies whatever we have discussed, the strengths and weakness are given. So, you may refer for each and every technology. So, sometimes what happens, we can combine two technologies as well. This is one of the such example. The product is pumped and it is sprayed using ultrasonic nozzle. So, this is what we have seen is the ultrasound technology, and then your pulsed UV light technology is used, right. So, combined both ultrasound as well as pulsed UV technology. So, this is the way you can increase the death of microorganisms, or sometimes you wanted to maintain certain sensory qualities of the food. So, this way you can combine both the technologies to achieve your goal. So, these are additional references and resources which you would like to refer whatever we discussed in the class, and mainly these tables were taken from those references. Okay, thank you.